Greetings, my statistics friends. This video is for Chapter 9, and we're going to work out problem number 5 from our homework set. And problem number 5 corresponds to section 9.3 and question number 12 from 9.3's homework. So we're interested in buying a new Lincoln Navigator or town car, and you are looking at different models with different options and the list price for the vehicles. The salesperson approaches us and you wonder what the dealer invoice price is for the model with this option. So the following data are based on random selections of these cars and different models and options. So why is the dealer invoice in thousands of dollars for the vehicle? So the idea here is that the input is how much money you spend on the vehicle, and the output is the amount of money that the dealer actually got the vehicle for. And so that's true for these 1, 2, 3, 4, 5 data sets. Okay, so the first thing we're asked to do is verify these numbers. And once again, you should verify those numbers, but those numbers are already here. So 195. So if I sum up 33, 34.1, 36.1, 44, and 47.8, I should get 195. And the same for 177.7. And so that is the first part per day. So you can verify those, but they indeed should be these numbers that are just up here. So the second part B says use a 1% level of significance to test a claim that this P, which is this funny looking P, is bigger than 0, and use 2 decimal places. So they're asking for the T value and the critical T. So let's go down to our calculator and let's figure out that T value. I put the values of X in list 1 and the values of Y in list 2. That's my common way of doing it. And then I go to statistics and over to test, and I scroll down to the linear regression t-test, which is F, and I hit enter. And I put the X stuff in L1 and the Y stuff in L2, and then the frequency is 1. And then there is this beta and this funny looking P, and we're supposed to do that our P, that funny looking P, is bigger than 0. So this right-tailed bigger than 0. So I hit enter there. Once again, I'm getting that from my question because it's asking me that funny looking P is bigger than 0. So funny looking P bigger than 0. And then I go down to calculate and hit enter. And when I do that, it gives me these numbers. And the first number that I want to write down is this T number. T equals 7.3131. So I go back to my problem. And so this T value to 2 decimal places would be 7.31. And my critical T, I actually have to use the student's T distribution table. Now remember, when we're using regression, we use an n minus 2 degrees of freedom. So n is 1, 2, 3, 4, 5. N is 5, so n minus 2 would be 3. And this is a 1%. So I look at my student's T table, and this is a one-tail area, since it's the right tail test. And I go over to 1%, so 1% is over here. And I go down to n minus 2 degrees of freedom, so down to 3. And I find 4.541. So the value that goes there is 4.541. So the 2 decimal places is 4.541. 0.054. Okay, so what's the conclusion I'm supposed to make? Well, I'm going to do it the traditional method, and I'm going to compare my value that I got, this p-value, 0.0026, with the alpha that I was given. And so what I'm asking then is 0.0026 less than or bigger than 0.01 alpha. And so 0.0026 would be less than 0.01 alpha. And so my alpha is 1%. Level of significance, right? So that's alpha. And the p-value of 0.0026 is less than alpha. And so when it's smaller than, I reject, right? I reject small things. So I'm going to reject, that's the idea. And when I reject, then there is sufficient evidence that, this funny looking p is bigger than 0. So remember what that means is I am rejecting the null hypothesis in favor of the alternative hypothesis that this value is bigger than 0. So that's my conclusion. This critical T would be used for what they call the critical value region method, and I will let you read about that in your book. So then it says verify that this S sub E is equal to these numbers, and then the A and the B is also equal. And I certainly could just retype these numbers in. So I could type in 1.6305, just copying it down, and minus 0.0361 and 0.9122 for sure. But let's look to see where we find those numbers at. So I look on my calculator again. And our calculator doesn't call it S sub E, they just call it S. So this is 1.63, which is this same number, 1.63. And then the A is, remember the form is the B is the slope times X plus the Y intercept, the constant A. So the A is negative 0.036, and that's what we have. And then the B is 0.9122, and that's what we have. So we verified that. And then it says find the predicted dealer invoice when the list price is $35,000. So when X equals 35, that's what we have to put in. So how do we do that? Well, we just type that X into our equation. So we got minus 0.036 as A, and our B was 9122, so 0.9122. So what I do is type in negative 0.036 and plus, so that's the A, and then plus the B, which is 0.9122, and I want to multiply that by 35 and hit enter, and I get this 31.891. So then in part D we type in that 31.89. So that's our predicted dealer invoice. When we input the sale price of $35,000, we predict that the dealer invoice would be 31.89. Now for part E. I think part E is the hardest problem that we have to do here because our Texas Instrument calculator does not calculate this. But this is one of those things we just have to write down the formula. So how do we find this confidence interval for Y when the input is 35? So how do we actually do that? Well, let's look at our formula here. So our error formula for the Y output, is the T sub C, the critical value for T, this SE, and then times the square root of 1 plus 1 over n plus, and then n times x minus x bar squared. divided by n times the sum of x squared minus the sum of x, all of those, squared. And remember that our t critical value for linear regression is n minus 2 degrees of freedom. So the first thing we want to do is find this t sub c. We already know the SE, and we already know the rest of these values, so we need to find this critical number t sub c. And so the question is asking us to find it at a 90% confidence level, and we have n minus 2 equals 3 degrees of freedom. So this is the critical line, this is the 90, and then we go down to 1, 2, 3 degrees of freedom, so 2.353. So that's our t sub c that we need for this part. That's our t sub c. Our SE we have already found. So that is 1.6305. We already know our n. Our n is equal to 5. And the x that they're asking us about will be for 35. The x bar, that's the average of the x's. Now we may not actually have that written down anywhere, but we can calculate that real quick. So I go to statistic and over to two variable statistics, and my x bar calculate. X bar is equal to 39. So now I have the x bar. And what else do I need? Well, I need the sum of x squareds, which we know what that is, and then we need the sum of x's squared. So let's type in all those values into our calculator. So here we go. We have 2.353 multiplied by 1.6305 multiplied by the square root of 1 plus, and then fraction bar, 1 over n, but n is equal to 5, and then plus fraction bar, n, which is 5, times, and then what's the rest of the formula? So 5 times the quantity x minus x bar squared. Well, let's see, x is 35, and then x bar was 39, so I need to put in a parentheses, 35 minus 39 in parentheses, square it, and in the bottom I put in 5 times, and then it's the sum of x squared. Well, the sum of x squared is 7775.86. So I'm going to put in 7775.86, close parentheses, minus, and then it's the sum of x's squared. So that's different than this, right? This is the sum of x squared. This is the sum of x's and then square it. So from here, the sum of x's is 195, and then I need to square it. So 195, and then I square it. And I hit enter, and I get this error value of 4.363. And so then to find the upper, well, I take the 31.89, that was my alleged output from my model that I'm going to get my predictor from my model, 31.89, and I'm going to add to that my error of 4.36. So 31.89 plus my error, and that is 36.25. Take that same number, 31.89, and subtract my error. So I'm just going to copy and change it to subtract and hit enter, and I get 27.53 for my lower. So in my problem, my lower limit is 27.53, and my upper is 36.25. Okay, so now let's move on to part F. So use a 1% level of significance to test the claim that beta is bigger than 0. The slope of the line is greater than 0. So the first thing I do is find this t statistic. Now we've already done this, but I'm going to re-show you how to do that again, because doing it for the beta and doing it for this funny looking p is exactly the same. So these two numbers are going to be exactly the same. So how do I do that again? I go to my calculator and I do statistic, and I go over to test and down to the linear regression t-test, and I put my x stuff in L1 and my y stuff in L2, and then this has the beta and this funny looking p, and there is not equal, less than, and bigger than, and we want the bigger than, and I hit calculate, and those are the same numbers that I got before. My t was 7.313, and so that's the number I'm going to put here, 7.31, which is what we did up here. And then at the 1% level of significance, I'm supposed to find this critical t. So remember that for linear regression, we use n minus 2. So we're using 3 degrees of freedom, n minus 2. And this is a one-tailed area, specifically the right tail. And the 1% is over here. So 1%, and I go down to 3 degrees of freedom. So 4.54 to 2 decimal places. So 4.54. Now those numbers are exactly the same as up in part B. We use the same type of thing. So when I did that, I got a p-value that was quite small. And so my p-value was 0.002, so 0.003, and that is smaller than 1%. So 0.2% is smaller than 1%, right? So I reject it because it's small, and when I reject it because it's small, I choose the alternative hypothesis. So I am going to reject the null hypothesis, and there is sufficient evidence that the slope is bigger than 0. That's what this means. And then now I'm to find the 90% confidence interval for beta and interpret the meaning. So let me go back to my calculator. My calculator knows how to do this. So I go to statistics and over to test and down to the linear regression t interval. This test for the beta, and so I want a 90% confidence interval, so I have to change this to 0.90. Your problem might be slightly different, but this one asks for 90%, so I'm going to calculate that. And it lists this confidence interval for beta. It also tells me the A and the B, and it tells me the degrees of freedom, which is nice. And then it tells me what the A is and the B are. So 0.61866 is my lower beta, 0.61866, and my upper beta is 1.2058. The lower to 3 decimal places is 0.619 to 3 decimal places. And my upper is 1.206 to 3 decimal places. And then I'm supposed to interpret the results. So there are two things that I want to point out here that that's beyond just interpreting the results. Remember that our beta is the slope. Anytime that we have a slope is equal to 0, we have a flat line. And for a regression curve, that's something we don't want, right? So we don't want a flat line. So we do not want a slope equal to 0. And so that's the first thing we can look for in the confidence interval of our beta, is 0 in between here. So if 0 is trapped in between that confidence interval, then that regression line is not any good. So that's we're 90% confident that 0 is not in there, which is a good thing. The other thing that it's telling us from our confidence interval is that there is a change, right? Remember, slope means change. So for every increase in the input, the output should have some relational change. And what is that relational change? Well, it's somewhere between 0.619 and 1.206. That's the change. And we're 90% confident of that change. So the interpretation is for every 1,000 increase in list price. So for every 1,000 increase in list price, the dealer price decreases by the amount that falls within the confidence interval, or the price increases. So does the price increase or decrease? Well, the slope is positive, right? So for every 1,000 increase, the price has to increase because the slope of this line is positive. We're 90% confident that it is. So it's not decrease, it's not decrease. So it's either for every 1,000 increase in list price, the dealer price increases by the amount that falls within the confidence interval, or for every 1,000 increase in list price, the dealer price increases by the amount that falls outside the confidence interval. Well, that's kind of silly. So for every 1,000 increase, we're 90% confident that the dealer price increases by the amount that falls within this confidence interval. If you have any questions, just let me know.